is non-magnetic. And as you can see, the slope in the first part is completely different from the slope in the second one. Because also the power depends on the penetration depth and on the resistivity. If you remember, the surface power that we are able to give to the workpiece is this one. So it depends on this one, this parameter, and this one. And these two parameters are completely different because this is delta. And you can understand that if the permeability is driving the behavior just below Curie, the main parameter driving the behavior and the slope above Curie temperature is resistivity. Okay? This is the main difference. The other very important part is the transition. As I told you in different lectures, the Curie transition is a sort of transformation with a latent heat of transformation. It means that I put some energy into the workpiece, but this energy is not translated in a temperature increasing, but is translated in the transformation of the structure of material. This is the reason why there is a part of the thermal transient which is completely different from the other. We can say that we have no slope, no temperature increasing, but also transformation. And the third behavior, which is really important, is the temperature difference. Because in any case, especially because at the beginning of the process the material is completely magnetic, we have a very small penetration depth. It means that the power density is mainly concentrated on the surface. It means that the temperature increasing on the surface is much more than the temperature increasing in the axis. So this is the behavior of the temperature difference, and during the induction through heating we have to take into account this temperature difference, and we must be able to control properly this temperature difference, because if this temperature difference is too much high, we can create some cracks in the billet. Okay? Perfect. So, but there are some solutions to these special problems, and the solution could be to use not only one inductor, like in this case, but some inductors. And each inductor can be used for a special phase of the thermal transient. For example, in this case, we use the first inductor for bringing the material to overcome the Curie transition. So, the first inductor is related to all the material below Curie temperature. Then we have a phase of equalization, so it means that this is time, this is temperature. Let me draw here one inductor, the second inductor, and so on. So, during the first inductor, we have a behavior like this one. Okay? We have a temperature increase both of the surface and the core. Then, we have no power. It means that there is a sort of equalization. And then we have the second inductor. and then an equalization again. So, by using a combination of inductors and space between inductors, we are able to control properly the temperature distribution in a different way, and to reduce also the temperature gap. The temperature difference in this case is not true, but the temperature difference between the surface and the axis. So, we will have such a kind of thermal transients both in a continuous movement of the billet and in a stationary one. In this case, for example, we use a stationary machine. We put the billet inside the inductor and we wait. So it means that in this case we are speaking about time. In this case it means that I switch on my inductor for a certain time, for example 30 seconds, then I switch off the inductor for 10 seconds, then I switch on again for 30 seconds, and then I switch off. This is the case because I take a billet, I put the billet inside the inductor, and I wait. But we can have the same thermal transients, and instead of having time in the x-axis, we have space. So, in this case, we are following this point, which is entering to the first inductor, and then moving the point, we are going to the exit of the fourth inductor. This is the behavior of the temperature of the point. Is it okay? So, it's very simple. Space or time. And this is the typical installation that you will have in order to perform such a kind of process. Usually we have the mains, then we have the transformer, rectifier, and the inverter. So, rectifier, inverter, compensation capacitors, load matching circuit, and then the inductor. So now we can go in deep with some theoretical aspects of induction through heating. We started from the same behavior of the power density distribution. We know that the power density distribution depends on the value of M. The value of M. But we realize immediately that both for lower values of M and higher values of M, in any case we have a non-uniform power density distribution. So we expect in any case both for M equal to 1, 2, etc. and for M equal to 10, 15, we have a power density distribution which is not uniform. So we expect a non-uniform distribution of temperature, and we realize that it's true. By the diagram that I showed you before, you can realize that the behavior of temperature distribution is uneven. The second aspect is the efficiency. We must be careful. If we would like to perform an induction through heating process, an efficient induction through heating process, we must care about the value of M. Remember, value of M be greater than 2.5. If we are below 2.5, we are using energy with a lot of losses. So, we can say that the workpiece is becoming transparent to the electromagnetic field. We must be careful about this value. Why? Because if it's quite trivial to guarantee the value of M greater than 2.5 below Curie temperature because of the magnetic state of the material, it's not so trivial to guarantee the same value above Curie temperature. So, we can have some calculation. Below Curie temperature, if we use the same frequency, and we'll see what I mean. If we use the same frequency, here we have, if we maintain these numbers like a constant, here we have 1/5, here we have 120. So let me say that there is a big variation of the penetration depth from below Curie temperature and above Curie temperature. And the driving parameter is mu. So mu could have high value up to 100 below Curie temperature and the one above Curie temperature. The resistivity has 20 micron per centimeter values at ambient temperature, 120 at 1200 degrees. What does it mean? That the variation of resistivity is much less important than the variation of permeability. There is not a proper compensation of the variation of permeability, the resistivity, with the variation of resistivity. The driving parameter is the magnetic permeability. Okay? So, we would like to be able to guarantee a proper efficiency both below Curie temperature and above Curie temperature. In order to do so, we must design or choose properly the process parameters above Curie temperature. Why? Because if we have such a kind of parameters able to guarantee a proper value of M above Curie temperature, we are sure that below Curie temperature we guarantee the same parameters too. Okay? So, the idea is, if I would like to design properly an induction through heating process, I have to design this process in hot conditions, not in cold conditions. Because if I choose the parameters in cold condition, I'm not sure that in hot condition I respect such a kind of boundary, such a kind of constraint. Understand what I mean? So, coming from this statement, this main view, I can try to put in a diagram the frequency, because you know the only parameter I'm able to choose is the frequency. Because if you remember, the diameter of the inductor is mainly due to the diameter of the billet. And as I told you the last lecture, we can choose, or better, we can find a compromise if we have to treat different billets with different diameters. I can find a compromise. I can choose a range of diameters, and then I use for the same range of diameters the same inductor. It's a compromise. Maybe the bigger billet will have a better efficiency and the smaller one a lower efficiency. But in any case, I have a range of efficiency, but in the same range I will obtain good values of efficiency. Okay? So let me say that it's not a variation parameter or a parameter that I can choose. But the only parameter that I have to choose properly is the frequency, because the material is the material. If I have a magnetic material with a certain resistivity, I can't change it. I have to treat this material. So the only parameter where I can drive something is the frequency. So if you look at the yellow table, let me say, I can't go down, or better, to choose values of m less than 2.5. It's the limit. Okay? So if I choose 2.5, I'm choosing the best frequency. With m between 2 and 5, we have a satisfactory efficiency, but for m greater than 7, we have low thermal efficiency. Why? Now we are speaking about thermal efficiency, not electrical efficiency. For electrical efficiency, I have already said that we have to stay at the values greater than 2.5, at least. But from the thermal point of view, let me say that m greater than 2.5 means a shallow distribution of the power density. So we are concentrating all the power density on the first layer of the billet. It means that we have a lot of losses outside the billet. We are not putting the power sources inside the billet, but only on the surface. So this is the meaning of the yellow table. So if we combine the proper conditions for high electrical efficiency, and we take into account also these considerations, and we do some algebraic passages from the traditional formulas, we can have a choice of the frequency between 3 and 6 ratio the square of the diameter of the billet. And this is these formulas are represented in this diagram. So the A and B are minimum and maximum values of frequency, and C is the optimum frequency. So it means that if I have a billet of a diameter of 100 millimeter, the minimum frequency must be 0.3 kilohertz. The maximum frequency will be 2 kilohertz. If we go, or better, if we choose a lower frequency, we have big problems because we have problems about electrical efficiency. If we go up, maybe we have some problems with the thermal efficiency. Okay? And in this band, we have the optimal choice of the frequency. This is from theoretical point of view. But there is another issue, which is the possibility to generate frequency, or better, to produce inverters for different frequencies. It's much easier to produce inverters with the frequencies above 2 kHz than below 2 kHz. And there is another issue, which is the noise. You know that our ears listen to the sounds up to 40 kHz. And the most boring sounds are sounds with very low frequency. Because of the vibration that the electromagnetic forces can produce during the heating, we prefer to use higher frequency instead of lower frequency. So, okay, from theoretical point of view, there are some possibilities to use frequencies below 2 kHz. It's not a problem. But from the practical point of view, it's better, especially for billet not so big, to use higher frequency, at least 2 or 3 kHz. Okay? Obviously, if you have such a kind of billets, so we are in the range of 200 millimeters, 250 millimeters, in that case, usually we use industrial frequency, 50 Hz, directly 50 Hz. So the choice, when you have an induction heating process, for big billets to use industrial frequency, 50 Hz, and for smaller billets to use frequencies at least of 2 kHz. So usually the process constraints are the temperature difference in the cross-section, the distribution and the control of induced power along line, the limitation of radial thermal stresses for certain state grades, and this is due to the temperature difference in the cross-section, and the other parameter is holding time above specified temperature for metallurgical transformations. For example, there are some special steels that they need to maintain a temperature above 1200 degrees for solubilization or some other heat treatments. So we have to take into account all these specifications. How we can choose such a kind of parameters? So this is very complicated. I will try to give you some, let me say, some ideas how to choose properly the time and the power. First of all, we are in an ideal situation. From the theoretical point of view, we are not taking into account the heat losses from the surface of the workpiece, from the surface of the billet. So we are speaking about an adiabatic process. And we are dealing with only one step heating. So secondly, in order to apply such a kind of formulas, we need only a non-magnetic material. So, let me say that it's a very simple case. an ideal case, but starting from these considerations, we are able to understand the behavior, or better, the behavior of the thermal transients related to the different parameters, and the choice of the two main parameters, which are the time, the power, with the constraint of temperature difference between axis and the surface. So, if we fix the temperature difference, this is a relative temperature difference. Zs minus Za ratio Zs. 0.1 means 10%. So if I have 1000 degrees on the surface, we have 900 degrees on the core. Okay? So this is the, let me say, percentage values of the temperature difference. And then, starting from this parameter, I can choose the time. The time T0 depends on the square value of the radius, all the thermal parameters, so C is the specific heat, gamma is the density, Q, and Zs, which is the surface temperature, and this formula, epsilon, is a prescribed value, because it's a process parameter. I would like to fix, for example, 50% of temperature difference between the surface and the core. It means that epsilon is 0.05. Okay, so it's another constraint that I fixed by design. We have to take into account the value of two special functions, which are called f of n. So, if you wanted to go in deep with these functions, you have to read the second part of the thermal transient. Do you remember? We dealt with the thermal transient related to the non-uniform heating. And then we spoke about induction hardening. The second part of the thermal transients was for uniform heating. By using some theory about the thermal transient for uniform heating, you can have such a kind of formula. Maybe you